This is the lesson on quadratics with complex numbers. All right, let's start with a review of how to simplify numbers under a radical. So here we have the square root of 108. We start by factoring 108 into pairs, and we look for the pair that has the largest perfect square. In this case, that is 3 and 36. 36 is a perfect square. So I'm going to rewrite my radical as the square root of 36 times 3. My next step is to break up the radical. Square root of 36 times the square root of 3. At that point, I'm just going to simplify the square root of 36, which you know is 6. And so we end up with 6 times the square root of 3. Now let's take a look at another example. The square root of 24. As I did before, I'm going to start by factoring 24. And I see that the pair with the largest perfect square is 4 times 6, because 4 is a perfect square. So I rewrite my radical as the square root of 4 times 6. And then I break that up into the square root of 4 times the square root of 6. Now, if you take a calculator and take the square root of 6, you'll see that it ends up being a long, complicated decimal. So that is not a perfect square, but the square root of 4 simplifies to be 2. And so we end up with 2 times the square root of 6. Pause now and make sure that you have both of these examples in your notes. Now, what does this look like if we're solving a quadratic equation? Well, I have one here, and as always, we're going to start by identifying A, B, and C. And then we're going to substitute those into the quadratic formula. Now, when you're simplifying the quadratic formula, always begin by simplifying negative b, and then simplifying the radical, and then simplifying the denominator. When we do that, we end up with x is equal to 18 plus or minus the square root of 260 divided by 2. Now, again, if you take a calculator and you put in the square root of 260, it's going to end up being this long, complicated decimal. That is not what we want. So we're going to factor 260 and find the pair that has the largest perfect square. And it turns out that that is 4 times 65. So we're going to rewrite that radical as the square root of 4 times 65. And then we're going to separate those two radicals and continue to simplify until we get 18 plus or minus 2 times the square root of 65, all divided by 2. At this point, I'm going to divide 18 by 2, and that gives me 9. And I'm going to divide 2 times the square root of 65 by 2, and that gives me the square root of 65. Now you'll notice here that I did not convert the square root of 65 into a decimal and divide that by 2. I left it as the square root of 65. In this case, we treat square roots that are not perfect squares as variables, the same as variables, and so you're going to leave it like that. Do not convert it to a decimal. Pause now and copy this example. Let's take a look at another example. We're going to start by identifying A, B, and C, and then substituting that into our formula for the quadratic formula, simplifying, and we end up with the square root of 160. Now, that 160 is not a perfect square, so we need to factor 160 and find the pair that has the largest perfect square, and that ends up being 16 and 10. And so we rewrite that as the square root of 16 times 10. Then we rewrite that radical as the square root of 16 times the square root of 10. Now, by now, you know that the square root of 16 is 4. And so we're going to simplify even further until we have 4 times the square root of 10. That is equivalent to the square root of 160. And now I'm going to break this fraction up into 2 pieces. I'm going to divide 8 by 2, and you know that gives us 4. And then 4 times the square root of 10 by 2, and that gives us 2 times the square root of 10. And so our answer is 4 plus or minus 2 times the square root of 10. Now, if you have questions on how that last simplification process works, be sure you bring those questions to class, and we can go over that in gory detail. Pause now and write down this example in your notes. Now let's talk about complex numbers, which include imaginary numbers. Now, what are complex numbers? They are used to describe solutions to quadratic functions that have no x-intercepts. You see this graph here that I included, it has no x-intercepts. So how do we solve something like that? Well, we would say that it has no real number solutions, meaning no solutions that are contained in the real number system, but they can and they do have solutions that include imaginary numbers or complex numbers. Pause now and write down the definition you see on the slide and sketch this graph. Now let's take a closer look at imaginary numbers. The square root of -1 is I, and the notation that we use is this lowercase I. If you square the square root of -1, you get I squared, and that is equal to -1. Now make sure you highlight those or star those, because you're going to need those as math facts a little later on in this lesson and when we're practicing in class. Now, how do we simplify something that has an imaginary number? Well, let's take a look. We start with the square root of -2. We're going to factor out the -1 so that we have the square root of 2 times -1. And then, you probably guessed it by now from our previous examples, we're going to break up that radical and end up with the square root of 2 times the square root of -1. Now up above here, where you see the highlighted area, you can see that we already talked about the square root of -1 is represented by I. And so we're going to continue with our simplification by changing the square root of -1 into I. Now, one thing to remember is that we never leave that I behind or after a square root. So I'm going to move it in front of the square root here, and our answer is I times the square root of 2. Let's look at another example, the square root of -4. As before, we're going to start by factoring out -1. Then we're going to break that up into 2 radicals and take the square root of 4, which is 2, and our answer then is 2I. Pause now and write down this example in your notes. All right, make sure you have this example for your notes. Now, let's take a look at a couple of more examples. Let's take a look at 5 times the square root of -121. Now, as always, no matter how big the number is under the radical, we start by factoring out the -1 and then breaking up the radical. And now we're going to look at the square root of 121. It turns out that is 11. And so we have 5 times 11 times I, which gives us our answer, 55I. Our last example in this area is the negative square root of -96. We're going to factor out -1, break up the radicals, and then factor 96. It turns out that the largest perfect square with 96 is 16, and those two factors are 16 and 6. So we can go ahead and break up those 2 radicals and end up with the square root of 16 times the square root of 6 times the square root of -1, which gives us -4 times the square root of 6 times I. Now remember, I said that we never leave the I after the square root, so we're going to move that in front of the square root and finish our simplification, giving us our final answer of -4I times the square root of 6. Pause now and copy down this example. Now, what does this look like if we're actually solving a quadratic? Well, I have a quadratic here, and we are going to identify A, B, and C and plug those values in to the quadratic formula and simplify. So here we have -10 plus or minus the square root of -4 divided by 2. Now we're going to apply what we just learned to help simplify this answer. And so we're going to factor negative 1 out of that radical, and then break that radical up into two pieces, the square root of 4 times the square root of negative 1. And then we're going to simplify those radicals further by taking the square root of 4, which is 2, and the square root of negative 1, which we now know is I. Now that we have negative 10 plus or minus 2i divided by 2, I'm going to take the one last step of dividing negative 10 by 2. That gives us negative 5, and 2i by 2, and that gives us I. Again, we treat I as if it were a variable. We're not going to divide the square root of negative 1 by 2 and get some weird imaginary decimal. We're going to leave it as I. Pause now and copy down this example. Now let's take a look at one last example just to make sure that when you're looking at your notes, you have a couple of examples of how to do this. So we have this quadratic, x squared plus 4x plus 12. Start by identifying a, b, and c. Now we're going to plug those values into the quadratic formula and simplify. And we end up with negative 4 plus or minus the square root of negative 48 divided by 2. Now let's address the negative 48. So we're going to start by factoring out negative 1, and we're also going to factor 48. The largest perfect square that is a factor of 48 is 16. And so 16 times 3 is 48, so we're going to have the square root of 16 times 3 times negative 1. Now we're going to break that radical up into 3 and break it up into the square root of 16 times the square root of 3 times the square root of negative 1. And then we start simplifying from there. Now we have negative 4 plus or minus the square root of 16, which is 4, times the square root of 3, which cannot be simplified, so it stays the square root of 3, times the square root of negative 1, which can be simplified to I. And we do not leave that I after the radical, so I'm going to move it in front. And we end up with negative 4 plus or minus 4i times the square root of 3, all divided by 2. And by now, you know I'm going to take that last step of dividing negative 4 by 2 and getting negative 2. And then 4i times the square root of 3 by 2. That gives us 2i times the square root of 3. And again, please note that I treated I and the square root of 3 like variables. I don't take them and somehow divide them by 2. I leave them as is in my answer. Then my answer is x is equal to negative 2 plus or minus 2i times the square root of 3. Now I know you probably have questions, especially on this last step of simplification, but whatever questions you have, make sure that you write them down in your notes and bring them to class, and we will address them then. See you in class.